Hello. Hello.
Yeah, we can hear you.
We can hear you, sir.
Yeah, I'm asking whether you have access to um, accounts on the LMS.
Yes, we have access to
Yes,
it.
we have, sir.
Okay, so that's good. So I want to just show you something. Okay. Give me a minute, okay? Okay. 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 So sorry about that. It's a little slow. Okay, so I don't know. Do you see this course in your LMS?
Yes, sir.
Okay, so let's open it and then I'll show you a couple of things. So we have some, I don't know if you are here, but if you are not here, kindly talk to them so that they can get you set up, okay? I have a listing of all of the course materials available over here so that you can get access to all of the material. This will be the list of topics that we will be going through over the period, okay? So basically, like I was saying earlier, my name is Mr. Bernard Buckman, and I will be taking you through programming, introduction to programming. This course basically introduces you to programming languages and the logic in creating programs or solving problems using programming languages at whatever level in your education. Once you are in IT, you need to understand some of the basic concepts so that when we teach you programming in the future, like C++ or like Java or like VB, you can understand how the logic, how to put together the logic, and then how to convert that logic into an actual programming, an actual program. Okay, so I'll teach you all the tools you need and give you the basic understanding of key concepts. Okay, so throughout the course, we will enjoy ourselves by going through or discussing some of the major things that we need to know with regards to programming languages. So please do take your time and then always check in on our course page from time to time, okay? I don't know why this is still here, okay? So today we will be looking at an introduction to computers because before you can understand programming, you need to understand properly what computers are all about and how they can used or how they can be used to provide to provide um, ample information or to provide what the users need. Okay, so may I ask from the house whether anyone has taken their time to okay, whether any of us have taken our time to look at our course page and the material on the course page. Yes, yes. Anybody? Hello? Can you still hear me?
Yes, sir.
Yes, sir.
Okay. The one way you can enjoy the class is when you make the class interactive. So please interact with me. Yes. Has any one of us, per chance, has any one of us looked at the course materials on the page? What is your general impression about the course? Hello? Okay. Mr. Richmond. Mr. Richmond.
Yes, good afternoon.
Yes, good afternoon, sir.
Yeah. Yes, I visited it yesterday and I downloaded all the course units that you posted, but I'm about to,
Material.
yes, please. I'm about to go through it. I saw about almost 8 units which we were going through. So
Okay.
that's what I've done so far. Thank you.
Okay. 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 That's cool. Okay. Okay. That's cool. Okay. That's wonderful. Okay. So we since Mr. Richard has accepted for us, we will continue and then we'll look at we'll look at introduction to structured program design and then introduction to programming as in an actual fact. Okay. So today our key things we will focus on, or key amongst the things we will be doing today, is to get a general review of what computers are and what programming is. And then we want to also be able to go through a brief history of computers, what they are, where they came from, what the history of computing is. And then we will look at a history of programming languages as well, because that's our main course. Programming languages is our main course, so we need to understand what they are and how to use them. Okay. Then we will look at basic computer components or basic components of a computer system, and then we will look at computer programs and software, and then look at computer programming and types of programming languages, and then language translators. Okay. Within the lecture, as we're having the lecture, if you have any questions, please don't hesitate. Just try as much as possible to um, let me know what your key issues or problems are. Are we okay? Are we okay? Okay.
Yes, sir.
Okay. So,
Sir.
is there a question? Okay. So, what is a computer? Okay. So, traditionally or initially, the word computer came from the concept of computer. Okay. So, it's a French word, and basically, what it simply means is that we want to calculate. Okay. It's a verb for to calculate. Okay, the need for computers came as a result of our desire and our need to do calculations. My friends, can you see my screen well?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir. Nice. It's better, sir.
Okay. Please, if there's anything I missed, you let me know, okay?
Okay, sir.
Okay, sir.
Right, sir.
I'm still experimenting with all of this, so you let me know. Let me see. Give me a sec. Okay. Okay. Friends, let me use this one instead. Let me use the tablet instead. Okay. Okay. Hope we can all see it. Okay.
Yes, this is better, sir.
Okay. So we will use this one and then we'll try as much as possible to. Okay. Thanks. Sorry. Sorry. Okay. Okay. So, like I was saying, the word computer comes from the Latin word computer, which simply refers to calculate. Now, human beings have always been looking for ways to make calculations as simple as possible. Today, we have number systems, we have algebra, we have calculus, we have integration. We've gone so far to do accounting, we have maybe cost accounting, we have economics. So we have all of these complex things which make our life easier. But things were not the same sometime, not too distant past. Okay. And as a result of difficulties in calculating, agreeing on how many things are in maybe and how many items are in a number, ensuring that there is fairness and all of those other issues may have resulted in some form of need or a desire to get some calculations done. Okay, so the word computer came about when they wanted to maybe express that idea. Now, fast forward in modern times, we have traditionally referred to the term computer to mean an electronic device. But we should remember that since the origins are coming or predating electricity, what it means is that when the first computers were built, there was no electronic device then. Okay, so it means that we had things like sticks, we had things like stones, we had things like tally systems. Okay, if you have been to JSS, I think when you were doing frequency number systems, you remember that thing we did, down, 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 across, 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 that kind of system. Okay, so all of those have helped to ensure that we are able to accurately calculate. So the more accurate definition of what a computer is that a computer can be referred to as a mechanical, or an electronic device that can store, it can retrieve that information that is you store, it can help you manipulate that information with something called software. Okay, so once the device can maybe help you store some information, retrieve some information, and manipulate that information, we refer to that device, whether mechanical or electronic, as a computer system. That is how come a calculator is a computer, and the phone you are holding in your pocket is also in your hand, is also a computer, because they can help you do any of these two. Now, it is also important to mention that, it's also important to mention that items or devices like sticks, stones that we use for tallying and all those things are also computers, because even though they don't have electronic components, they have a way to help the user store some numbers. Okay, so for example, if you're at a workshop, or a warehouse, and you don't have an electronic computer, and you have things coming in, usually what they do is that they pick a pencil or a pen or maybe some sticks. Then once a specified number of items pass, they perform an operation by adding one of the sticks or one of the stones to the existing ones which have been there or which are there from the previous calculation. Okay, so that is what a computer is. Now, because we have electronic computers, okay, we can also say that for an electronic computer, the thing that will make us be able to do this calculation and all of these things is the software. Okay, and the software is written using a programming language. Okay, so the software is a sequence of steps that are used to what? That are used to instruct the computer to do specific things. Okay, so that is what we mean by computer, and that is also what we mean by software. Computer is a mechanical or electronic device for manipulating, for storing, for retrieving information. Okay, and then the thing that makes you be able to manipulate is the software. So it consists of sequence of instructions that tell the computer exactly what to do. So when you start WhatsApp on your phone, WhatsApp tells your computer or your phone how to take the message you have typed and then send it to the next person or the other person on the other phone, wherever they are around. Okay, now we can go in there and see several different definitions, but our course mainly is focused on structured programming or introduction to programming. So we want to stick around programming. So it is important, but it's important to understand that computers can be classified based on the generation. So we have a generation where we started computing where there was nothing, there was no electricity. We just started it with what? Mechanical things like sticks and stones. And we built on that. We built on something called the Pascaline. We built on that. We built the analytical engine. We built on that. We had electricity. We built the ENIAC, the EDVAC. We built the ICA system. We built so many computers, and today we have maybe a modern tablet or a modern iPad or something. Okay, so they can be classified based on the generation that you find them in. They can also be classified based on the type of computer. So sometimes we have computers which are built for personal use. We call them PCs. Okay, PC, personal computer. A personal computer has the capability to help you, the user, perform work individually on the computer system. Then we have some which are very powerful, which are maybe not meant for just one person, but they can do very powerful work as well. They are called mainframe computers. Then we can have maybe a class of computers which are a bit more sophisticated than mainframe, but are not too powerful that they are supercomputers. Okay, we call that one server computers. Okay, so we can have computers in different categories or classes. Now, where did computing come from? So we don't know specifically who can say that to compute or to calculate came from them, but we have an understanding of where exactly or when exactly mechanical devices started coming up. Okay, so sometimes we can say that before the 1800s, okay, what happened was that we used to have tools like the abacus, tools like sticks, tools like stones, chalk, and the like for doing calculations. Because ideally, we are saying that computers or to compute means to do calculation. So we wanted to aid human beings to do calculations. And so we use the abacus or the sticks or stones. Then somewhere in between that period, 1800 and the 1900s, what happened was that we had instruments or tools like the Pascaline developed by an author or developed by an inventor called Blaise Pascal. Okay, he designed something called the Pascaline. Then we had Wilfred Leibniz. Okay, he's a German scientist, and he developed something called the step reckoner. Okay, then we had a famous British mathematician inventor called Charles Babbage. So Charles Babbage is known for his invention of the analytical engine somewhere in the 1837. Okay, then Herman Hewlett, okay, the founder of Hewlett Packard, okay, HP Computers, the founder of HP Computers, around somewhere in the 1896, because of a U.S. census, he founded or he worked with a company, IBM, to develop a machine called the tabulating machine. This is a calculating machine. It doesn't look like today's modern day computers, but it is a calculating machine and does the job like a modern day computer. Okay. Okay. Now, going fast forward, when electricity began and then analytical engine from there, around 1930s, there was an American scientist called Vannevar Bush who led a team to design something called the differential analyzer based on Charles Babbage's work on the analytical engine. Then Konrad Zuse with the German Reich in 1930 designed something called the Z1. In fact, he had a sequence of Z's. We had Z1, we had Z2, and then the final one was in Z3. Okay, so these were perhaps the world's first functional computers. Okay, and they were also programmable as well. This was built somewhere in the heat of the Second World War. Then somewhere in the 1937, thereabout, we have Hewlett Akins and his team. They built an electronic device we call the Wk1. So Wk1 can perform calculations, but it was not recognized as the modern day first mechanical or electronic computer. That title was given to a machine called the electronic numerical integrator and computer. And this was perhaps maybe the first general purpose electronic computer designed somewhere in 1946. Around 1951, John Mauchly and Eckhart Presper designed something called the UNIVAC. So the UNIVAC was one of the inventions after the discovery of modern day computing. Okay. Now, at this time, computers were using something called vacuum tubes. They were using something called vacuum tubes. And vacuum tubes were unreliable, okay? So vacuum tubes were unreliable. The fact we're saying it's unreliable means that they had a lot of inefficiencies. For example, if they were working and the light went off, or any of their components overheated, and one of the vacuum tubes blew up, the computer will have to be stopped, and then we'll have to fix that problem and then restart the entire process again. So it created a lot of redundancies, and because of that, they started developing something called transistor to replace the vacuum tube. So this was done somewhere between 1956 and then 1963. Since there are many different private manufacturers who are claiming ownership of the discovery. Okay. Then fast forward, we had ICs, integrated circuits. Okay, so integrated circuits are just the same as transistors, but what they are is that they have a transistor can carry just one. Okay, So transistors normally look like they are 3-pin devices, okay, with a box on the top and looking something like that. And then sometimes they have a live, neutral, and a ground, okay. So they wanted to put more transistors into one circuit, so they built something like that. So you see normally on the board, it looks something like a caterpillar, okay. It's a black electronic device that consists of several transistors all built into one. So we call that integrated circuits, IC. Okay, and ICs now allow us to, instead of having one transistor for every single thing, okay, so one transistor, maybe if a computer will require 20,000 transistors, you have to get 20,000 transistors. But here is the case where you have reduced the size or reduced the work of the transistors. Okay, so once you reduce the size or you reduce the work of the transistors and you put about 100 or 200 transistors into one IC, then there's no need to build a very big computer. You can use a very small computer, okay? You can use a very small computer or build a very small computer because about 1,000 or 100 transistors have been put into one IC, okay? Then we were able to invent something called the microprocessors around 1971. So these are exciting times in the history of computing or electronic computers as we know it. Then Apple in 1977 built personal computers for homes and for various schools and offices. Okay. Then IBM also came into the race somewhere in the 1981, and then they built what we call the personal computer, the PC. Okay, so PC is actually a term coined around IBM to make it possible to build or buy a computer from one company and fix other components into that computer. Okay, so they are compatible with other components, whereas that of Apple is not compatible with other components. Okay, now let's look at a brief history or some of the major timelines in programming. So from the very start, programming has been developed side by side with computers. Okay, so even the mechanical computers in 1843, Ada Lovelace was an assistant to what's his name? Ada Lovelace was an assistant to Charles Babbage. Okay, so Ada Lovelace wrote a paper, a famous paper, which is described as the first computer algorithm. Okay, and in that paper, she describes the formal recipe or process for designing or how to make the analytical engine perform the computations or do some calculations. Okay, now we can describe this algorithm Ada Lovelace wrote as one of the first computer programs. Okay, then Conrad Zuse in 1941 thereabouts also wrote a similar program for his Z3 machine, right? It's a German word. It will be difficult for me to pronounce, but you can see that word over there. You can try and pronounce it. And that is described, that's the name he gave to the programming language of sorts that he's describing his algorithms in. Okay. And then we saw the need to simplify things. And so one of the first programming languages that we needed was something called an assembly language. Okay. And once you had assembly language, now you can build something on top. And so we built what we call Fortran. Fortran is one of the first few languages designed. Fortran stands for Formula Translation. It was built for business and web business applications. Sorry. Then in 1958, a programming language called Lisp. Lisp is an AI logic-based programming language. Okay. Then we had languages like COBOL. COBOL came somewhere in 1959. It was designed by a famous American herself called Grace Hooper. And then in 1960 thereabouts, we had Algo and Basic. Okay, these ones were also designed in around 1960s to 1970s. Then C was designed in 1972. C was created by Dennis Ritchie, and very nice programming language. You should learn it before you leave school. Okay. Then in the 1980s, we began a paradigm called object-oriented programming. And so object-oriented programming allows us to build programming languages around a concept called classes, okay? Around a concept called classes and objects, okay? So one of the first programming languages to enable us do something like this was C++. Okay. Then Python was designed sometime in 1995, 1990, sorry, thereabouts. And then in 1995 we have Java and JavaScript. And then today we have hundreds and hundreds of programming languages. Examples of such programming languages include Ruby, Ruby on Rails, PHP, Swift, Kotlin, and so many other programming languages, Carbon, and so many of them have emerged over the years. Okay, so you find out that there are hundreds of programming languages available for anyone who wants to learn and use them, Any questions so far about the history of programming? Any questions so far? Okay, so if there's no question,
Hello,
we
sir.
all understand. But please, if you have a question, kindly put up
Hello.
your hand, or you can send a question through the chat. Okay. Okay. Since there's no question, we will proceed, and then we'll proceed with that. So, before you can program, we need to understand also what we are going to program. Okay. So, in order to understand what we are going to program, we need to know. We need to know the basic components of any computer system. So when you pick any computer system, whether your phone or your wristwatch, your Android watch, or your Android TV, or your Android car, or your any computer whatsoever, you see some of these main things. We are not saying that they must be there by force, but we are saying that you likely see them. The possibility of you seeing them is high. Okay. Now, number one, you see some devices called input devices. Okay. So usually these are the devices that allow us to enter information into the computer. Who can help us with some examples of input devices?
Sir.
Yes, sir.
Sir, mouse.
Pardon?
Mouse.
Mouse. Yes, thank you. Prince Owusu, okay, henceforth.
Hello, sir.
Yes, sir.
I'll say keyboard.
Thank you very much. Keyboard. So we have mouse, we have keyboard, we have scanner, we have camera, we have microphone, we have fingerprint reader. We have so many devices. All the devices that allow us to enter information into the computer are regarded as input devices. Is that okay?
Sir.
Yes, sir.
Okay. Then the second issue are what we regard or call output devices. So an output device is simply a device that the computer uses to communicate with the user. Okay? Because once you give the computer something to do, it must tell you whether what gave it to do was successful or was not successful. Are we okay? Okay. So output devices include things like what? The projector. Currently, I'm sure most of you are listening to me. How are you able to hear me from your phone or from your laptop? The microphone. So the speaker. So the speaker on the phone or the laptop is enabling you to hear my voice. Then we have examples of output devices like the touch screen. Okay, the screen you can see the information, you can watch the information on the screen. You can also hear the information. You can also project the information with a projector. You can also decide that, oh, I want to print the information. How do you print information? You print it from a printer. Then, when or if you want to store information for a long time, okay, notice that with our modern day computers, when you turn off the computer and you had maybe a TV show playing, when you turn it back on, you don't see the TV show playing again. Instead, you see maybe the computer starts up fresh. Okay, or for example, maybe you have some Word document. You had it running on your computer, but because you didn't save the Word document, when the computer goes off and you manage to restart the computer, you will still not be able to see the Word document again because you did not save the Word document. Okay, so the part of the computer which can store or save information permanently is called secondary storage. Okay, examples I've already mentioned include what? The hard disk, your pen drive, the pen drive in your hands is a secondary storage. Sometimes people buy CD, disk, and CD. So that one too is an example of secondary storage. Okay, then we have a part of the we call the processing unit. That is the main brain of the computer system. Okay, so we have a part of the computer called the central processing unit. Most people refer to it loosely as CPU. Now, what the CPU does is that the CPU has two main components. Number one, we have a component called the control unit. Control unit is responsible for controlling everything about or on the computer. Okay. Then we have another component called the ALU. ALU stands for arithmetic logic unit. Arithmetic logic unit. Now, what the arithmetic logic unit is that it does all the calculations by the computer system. Okay, so if you need to do any calculation, it is the job of the ALU to do the calculation. But you need a device to control the computer. So the control unit controls together. The two things come together to form what we call the central processing unit. Okay. Then last but not the least, you need an area where you can store information until the computer goes off. We call it the centralized memory. Okay. Centralized memory, or what we call the primary memory, is responsible for that. Some books also refer to it as the main memory. Now, the only perk about this is that when you turn off the computer, main memory will go off. Unlike secondary memory, which keeps the content, main memory does not keep the content when you turn off the computer. Okay. Secondary memory is sometimes referred to as non-volatile. Okay. Because of this main issue. So non-volatile means that the thing does not break easily or is lost easily. But main memory is called volatile. Okay. Volatile means that the thing gets broken very easily. Okay. So what it means is that once you turn off the computer, everything in main memory goes off. But when you turn off the computer, the things inside the secondary storage do not go off. Any questions, my dear friends? Hello, any questions?
Question, no question.
Okay, sir. So CPU, input and output, main memory, and then input and output. Okay. Now, let's go back to programming languages. And so when we come back to programming languages, we see that now, like I said earlier, what's a programming language? Okay, or what is a program? Sorry, what's a program? So a program is the sequence of instructions which tells the computer how to perform a specific task. Okay, so maybe we want to do word processing. How do we perform word processing? We need a program to tell the computer how to do the word processing. Or maybe we need to do short, how do you call it? We need to do instant messaging. I send you a message, you send me back a message. I send you a message, you send me back a message. We call it instant messaging. So in order to do that, we need instructions, a program which will instruct the computer about how to do instant messaging. Okay. Now, there are two main types of programs. We have system software and application software. So let's look at system software since it's very easy to understand. Now, system software is the software which, sorry, guys. Sorry. Software which coordinates and controls all operations of the computer. So in order for the computer to turn on, to turn off, oh, why? Going back. Okay. Sorry. Okay. So in order for the computer to turn on, to turn off, to go on and off, and then maybe deal with memory, deal with battery, overheating, charging, connecting to the internet, disconnecting, turning off Bluetooth, sending a file, receiving a file, all of those things are managed by the system. We call that system software. Okay. The main examples of system software include something called the operating system. So the operating system is the program that manages your entire computer. Okay. Then we have other programs like utilities. Utilities are, or they do things like sound, manage network, maybe keyboard. Yes, sir. Hello.
Sorry, sir, it was a mistake.
Oh. Manage keyboard and all those things. So that programs that do that kind of coordination and control of the computer system are called system software. Okay. So examples of an operating system, okay, or of operating system are what? Microsoft Windows. So we have Microsoft MS or Windows 11. Oh, you cannot hear me? Hello?
I can hear you, sir. I can hear you.
Then why
We can hear you.
cannot hear me?
We can hear you, sir.
Someone just sent. Okay,
Yes,
says what? Please mute your mic. I can barely hear him. Oh, really? Mr. Jonathan, can you hear?
yes, I can hear you now, but the other sounds were disturbing the sound.
Okay. Okay. So we have Windows 11, Windows 10, Windows 8, Windows 7. Okay, we have something called Windows Vista. Okay, all of those are examples. We have Microsoft, we have a Macintosh OS or Mac OS. Okay, so we have other things, other OS like Ubuntu, we have iOS, we have Android. Okay, we have Android, we have several versions of Android. We have Android 24, Android 28, we have Android 11, Android 5, so many of them. We have Raspberry, Raspbian. Okay, and we have so many examples of system software. Now, the other kind of software that we can also write are called application software. So these are programs that instruct your computer to do specific things. So these ones, they instruct your computer to do specific things. Okay, so for example, I want to do instant messaging. Then I specially create an app for instant messaging. So I get WhatsApp. WhatsApp does instant messaging. Okay. Then maybe I specifically need an app for Word documents. Then I create Microsoft Office Word. So notice that Microsoft Office Word does not do the job WhatsApp is doing. No, it only does word processing and everything around word processing. Okay. So those ones, they do specific tasks. Now, when they do that, they allow the user to be very productive. Okay, so you can solve problems easily. It will supply you the information you need, and it provides you some entertainment, and there are so many benefits, right? Examples of such programs include what? Word processing software, spreadsheet software, photo editing tools, instant messaging tools. We have browsers, we have video games, we have so many examples of application software. In fact, apart from the operating system and the drivers or utilities, everything on your computer may be an application software. Okay. Now, what is the relationship between software or system software and application software. Somebody might ask, what's the relationship? Okay, so the key thing is that we need the system software so that our computer can function. Without the system software, you cannot turn on your computer. Your computer will be off perpetually. Without your Windows operating system, you cannot turn on your computer. You can have WhatsApp on a pen drive, or you can have maybe the setup for maybe Microsoft Word. But if you don't have Windows 11 installed first, you cannot install the WhatsApp or the Windows, or the Microsoft Office. Okay, you need the system software to be running on your computer before you can install the application software. System software manages the hardware, whilst application software makes you, the user, productive. You can have the system software, but if you don't also install the application software, nothing will happen. Your computer will just be an empty machine. Okay, so that is basically what the key relationship between system software and application software is. Now, let's come to programming. So now that we understand that these software are written or are just pieces of code, okay, written to tell the computer what to do. Now, the act or the science or the process of writing this software is what we term as programming. Okay, so programming is basically the process of solving problems, okay, by writing the software. Okay, and how do you write the software? We use a particular programming language. Okay, so normally before you can write a computer program, you need to understand how to solve problems. You need that information, or that understanding is very important. Okay, let's proceed. Now, we can write programs in different programming languages, which fall into one of four main classes or types. First one is called machine languages. Second one is called assembly languages. And then the third is called high-level programming languages. And the final one is called scripting languages. Now, the first two put together are called low-level programming languages. The first two are called low-level programming languages. So machine languages and assembly languages are also called low-level programming languages. Okay, so generally, you have about three main classes. Okay, now let's look at them one by one. So when we pick machine languages, we want to understand what machine languages are. We see that machine languages consist of code that the computer is capable of understanding at the hardware level. Okay, that's why we say the computer can understand it directly without translating. Remember, when you open a computer, you see a circuit board, some wires, some components you don't even understand, and those things. Okay, so the programming at that level controls those things. That programming is a little bit difficult than the one that we are going to teach you. Okay, so that one at the hardware level, we call that type of programming machine language programming. In fact, machine language programming is machine specific. When we say machine specific, it means every machine has their own programming
language at that level. Okay, so for example, if I have an HP, my HP's machine language is different from your Dell computer's machine language, because HP is built by HP, okay, Hewlett Packard, and then maybe Dell is built by the Dell Corporation. They don't collaborate in any way whatsoever. So they will build their own machines and put programming at the hardware level. And then HP will also build its own machines and put programming at the hardware level. Now, already, I can imagine that you are seeing the difficulty. The first difficulty about this whole issue is that, number one, because if you want to now learn machine language, you have to learn that of Dell. You have to learn that of what do you call it, MacBook. You have to learn that of maybe IBM, Lenovo. You have to learn Acer. You have to learn different programming languages for different types of hardware. And even with that same hardware, after some number of years, they will want to add some features. And so they will design a new machine which has a different machine language. Every machine model has its own machine language. And so it is difficult to teach people at that level. And it's also very hard to understand at that level. At that level, the programming, usually over there, we call that programming bits. And there's an example. So you have 0, 1, 0, 1, 1, 0, 1. So something like that is what happens at that level. At every 0, we go off, okay? And at every 1, we go on, okay? So you normally have something like that happening at that level. Then, because the 0101 is hard to understand, we designed assembly languages. So what is an assembly language? An assembly language is also a low-level programming language, but instead of using maybe zeros and ones, okay, we said that, okay, because a particular sequence of zeros and ones represents maybe an addition or a subtraction or a division or something, we will now, instead of writing the zeros and ones, we'll rather write the add and then give it the two numbers we want to add. Now, when we give the computer this information, the computer itself will now translate that information into zeros and ones, run the outcome or run the program, and then return the answer to us. Okay, so notice that we don't have to now learn zeros and ones like we do in the machine language level, but instead we have to learn the commands. Things work the way they are supposed to work. We call them opcodes. Okay, we call them opcodes. Operational codes and the rest. So they are a sequence of what? Mnemonic instructions. Okay, so they represent every add or subtract or divide or multiply or move or load represents some zeros and ones that are possible on that particular computer model. Okay, we have some examples over here to show you. Now, because the programming at that level is not done in machine language, we have to translate the add and subtract and all the rest. We have to translate them from English to zeros and ones so that the machine can understand the zeros and ones. Okay. Now, the program that will do the translation is called an assembler. Okay. So an assembler is responsible for translating the assembly language code into machine language code, and then from machine language back to the user. Okay, so this one is easy to read, but you need some extra work. The extra work is that you need to translate the code from English to zeros and ones. Okay, then because that one is hard to teach everybody, we build something on top of that one called high-level programming languages. So with high-level programming languages, what they are is that they are written to be easy for people to read, understand. All you have to do is to understand the logic. Once you understand the logic, you get an idea about how to piece together your program, because your program looks almost like English language statements. Any questions?
Hello, sir. Hello.
Are you okay?
Hello, sir.
Yes,
I have
sir.
a question.
Yes, sir. I'm here. You have a
Okay,
question?
so yeah,
Okay.
I wanted to ask why the name low-level programming languages and high-level programming languages.
Oh, as for the why, I do not know, but like I explained earlier, low level is at the hardware level. So I guess that at the hardware level, maybe there's a stack of hardware, okay? Hardware, and then maybe the software, okay? So maybe they thought that maybe at that level it's low. So because it's low, then the name low. And then the one on top of that one is, because that one is low, then that one is high. You understand? So as for the name, it will be hard for me to know exactly what the name is, but we all understand why it is named that way.
Okay, thank you, sir.
You're welcome, sir. Yes. Any other question? Okay.
Yeah, sir,
Okay,
please
so
can you hear me?
yes, I can hear you, sir.
Good. Yes, I want to find out when you were talking about the assembly language, you mentioned that
Yes.
when the language is in English, whereby you need a assembler to translate.
Yes.
Good. And I want to find out the assembler is the same as the interpreter. Sorry, the translator, as we normally find the other high level language.
Yes. So the translator of the
Thank
assembly language or the low-level assembly language program is called an assembler. The translator,
Okay.
it translates what you write in English into zeros and ones. Remember always that at the hardware level, the machine does not understand anything apart from zeros and ones. So you always need a program to translate the instructions from English or from whatever code you are writing into zeros and ones.
Okay. Thank
Okay.
you. Okay, sir.
You're welcome. You're welcome. Okay, let's go on. If there's more, you just raise your hand and then we can answer it. Okay. Now, so high-level programming languages are more like the English statements we write, but the key thing is that they have logic. Okay, so there's logic to help us construct meaningful statements. Okay, else people will write them like essays. Okay, because we don't want, maybe that is hard to write it like an essay, so we have it in logic. Okay, so examples include program languages like what? Pascal, we have Fortran, we have Lisp, we have C++, we have C, we have COBOL, we have Java, we have JavaScript, we have Python, Objective-C, Cocoa, Lava, F sharp. In fact, we have so many. Like I said, there are hundreds and hundreds and hundreds of them. I don't know whether they number into 1,000, but I know that they number in the hundreds. Okay. Some of them are publicly available for free. Others too are paid for, or special programming languages designed by special teams of people. Okay. Now, why do we call them high level? Because the features is what makes them high level. So number one, a key feature of high-level programming language is that the programming language needs to support abstraction. So abstraction simply means that we hide the underlying details from the user. In this case, the users are the programmers. Okay, so we don't want the programmer to worry about whether the machine is a dual core or hard core, quad core or oct core, or whether the machine has 400 gig RAM or no. That one, leave it for the programming language. All you have to do as a programmer is to write your programs. Okay, so you learn your logic, write your programs, and once you write your programs, that's it. That's the only thing you as a programmer need to worry about. How to write your programs. Okay, so we call that feature abstraction. We hide the way the hardware or the way things work, so that you are only concerned about your programming that you are doing. Okay, in the future, when you begin to learn programming, you notice that, oh, you are just learning the syntax, and then once you click on run, whether you are on Linux or Windows 7 or Windows 10 or Acer or Dell or HP, wherever you are, once you click run, it runs. You don't worry about how it is running, but you know that it will run. Okay? Then high-level programming languages are more readable. You can read them. In fact, you can understand what you are reading. But if I give you assembly language code, you may not understand necessarily what you are doing. Okay, so they are readable. Okay, so you can read them. Then the next key thing is that they are portable. Okay, portability here means that whether you are running a Dell machine or an HP machine or a MacBook or maybe an Android device or a tablet, you can write programs on either of these devices. Okay, portability could also mean that whatever platform, whether you are on Windows or on Mac OS or on Android or on any of other platform, you can still write maybe C++, or you can write C, or you can write whatever it is you are working on. Okay. Then the next key thing is that they make the user productive. The programmer, instead of learning assembly language code or low-level programming language code for only one machine, okay, you will be learning a programming language that can run on several machines. Okay, you don't worry about what machine. Once you pick the machine, you install maybe C++ or C, and you begin to write C. You don't care. It runs on the machine. Okay, that's what we mean by productivity. And then they have some other features like modularity. Okay, you can break the program down into units. You have data structures for doing different things. Maybe you want to manage strings of things. You want to manage classes of things. You want to manage objects. You want to manage maybe integers. You want to manage decimals. We call that kind of idea data structures. Okay. Then most of them have something which is so important today, which we refer to as what? User interfaces. Okay. Now today, I'm sure if I give you a laptop and there's no the Windows running on it doesn't run a user interface, but instead runs a command line, most of you would not appreciate the laptop very well. Okay, so most times programming languages which are high level, they are more friendlier to look at, okay, than their counterparts which are low level programming languages. Okay. Now there's a catch. The catch here is that high level programming language, because they are high level and they are not written in zeros and ones, but they are written in English and using logic, you have to translate them as well. So you need a translator. The code that you are writing is called source code. And then when you finish writing and you run the code now becomes binary code or object code. Okay? Now, there are two main classes of translators in high-level programming languages. We have interpreters, and then we have compilers. So I will explain what the key difference between the two is. Okay? Now, number one, so when we say the high-level programming language uses a compiler, or the high-level programming language is compiled, what we simply mean is that in the course of translating the source code, when we are translating the source code or the program you are writing, when we are translating it into machine code, we will pick the whole code and translate the entire code into machine code. Okay, so a compiled or a compiler translates the code written in one human readable programming language into machine code or another low level language at that a computer's processor can execute directly. So basically, we pick the entire code or the entire program and then we translate it completely before we begin. Okay? So the analogy is like you going to church. Most of you went to church today. I'm sure when you went to church, maybe you speak maybe English, but you went to a tree service, or maybe you went to the mosque on Friday when you were fasting. Even though maybe you speak English, the imam is speaking Hausa, then we'll have a translator. So what happens is that when the imam says his whole sermon, he will say the whole sermon. And when he's done saying or speaking the whole sermon, the translator will now translate everything that the imam or the pastor has said into English for you to understand. That's what the compiler does. It translates the entire program from one source code or one source language into a target or object language. Examples include Ada, Algo, C, C++, C Sharp, Objective-C, Swift, D, Cobol, Java, Basic, Clio, Crystal, Eiffel, F Sharp, Elan, and all the others. In fact, how you can know is that when the computer compiles the program, then we can say that that program is a compiled programming language or uses the compiler translator. Okay. The next key difference is the interpreter. So with the interpreter, we don't translate the source code directly into the object code, but instead of translating the source code into the object code, we take the source code and run it inside a virtual environment. I believe most of you have heard about this term VM. I think most of you have heard about VM. So this will create a virtual environment and the code is run inside this virtual environment. The code is not translated directly for the machine, but it is given to the virtual machine to run instead. Okay, so we say that interpreters translate and run the code line by line or statement by statement at runtime. Examples include APL or Apple. Okay, we have Basic, we have Lisp, we have Octave, we have IDL, Mathematica, MATLAB, JavaScript, Lava, GameMaker, Perl, Smalltalk. In fact, we have so many of them too as well. They are very cute or simple programming languages, which can be very sophisticated as well. Okay. So below here, I have a table of two different or key differences between compiled programming languages and interpreted programming languages. With a compiler, like I said, the compiler takes the entire source code and translates it into an object file, whilst the interpreter, it translates the source code line by line, or appears to execute the source code line by line or statement by statement. Another key thing is that the interpreter also takes less amount of time when it is trying to do that, because it's doing it line by line. But overall, it is a bit slow. But the compiler, because it is compiling the entire source code, it appears to be slow, but overall it is faster than the interpreter. Okay. Now, the interpreter does not produce an intermediate code, but the compiler generates an intermediate code. Intermediate simply means that when we are translating, can we leave the translated code in a middle form, or in a way which is not the last step, but it's close? Okay. So interpreters cannot do that, but compilers can do that. And then interpreters continue translating the program until the first error message is met. Okay. Then they stop and then they wait for you to debug. Okay. What it simply means is that, for example, if I'm speaking, I have maybe 10 lines of a statement and I'm speaking those 10 lines. If maybe I get to line 2 and there's a mistake on line 2, even though there are 10 lines, I cannot go to line 3 and go and continue. I have to wait for the mistake to be corrected on line 2 before I can go to line 3 and then line 4 and then line 5 and then so on and so forth. Okay. But with the compiler, you can translate the entire thing and then it will tell you that there's an error in one of the lines. Okay. So, and that's one of the key differences. And then we have some examples down here. Now, the last bit is that there's a group of high-level programming languages we call scripting languages. Now, most programming languages, we cannot write them inside other programming languages, okay? So scripting languages are designed so that you can write them inside other programming languages. That's one of the features of scripting language. So an example is HTML. When you write or design a web page, you use a language called HTML. Inside that same HTML, you can write something called CSS. It's also another language, right? It stands for Cascading Style Sheets. Then inside that same, you can write something called JavaScript, okay? So JavaScript too is another programming language, but you can write it inside HTML, okay? And then you can have Python. You can even write Python inside, okay? You can write PHP inside. In fact, you can even write Perl. You can write Perl inside. So you see that one programming language, you can write so many other programming languages inside. That's what we term as a scripting language. All scripting languages are interpreted. Okay. So we've come to the end of the slides, but we want to ask if there's anyone here who did not understand anything we did, or there was a particular or peculiar question.
Hello, sir.
Yes, sir.
Yeah, so in your previous slide, I think the slide 28, the last one.
The slides are
No,
only
28, sorry.
okay. This one.
Yeah, so I can see Java fall under the interpreter, but what I know is that Java is a compiler programming language.
Java is compiled and interpreted.
Okay, okay.
So some languages use both because there are different advantages of using either of them. Okay, so some languages
All
use
right.
both. Java is an example of a language which is first compiled, then it is interpreted. Okay, thank you. Mr. Gilbert Mensah.
Yeah, say, please, I wanted to know that the assembler only translates only the assembly code or any other codes.
Assembler only translates an assembly code for a specific assembly language. Okay, so an assembler, for example, if I have an assembler, okay, assembler code, and then I have a program, I have a computer, maybe a Dell computer. The program I write for the Dell computer's assembly program will be different from the one I write for an HP or a Lenovo. The Lenovo assembly language code will be quite different from the one I write for the Dell. Okay. And then sometimes Lenovo will maybe change the way the design or the model is. Once they change, they also change the assembly language. And so the one for the old Lenovo will not work for the new Lenovo. Okay. But there's a way that the manufacturers make things so that it's easy for them. Okay.
Okay. Thank you.
Welcome, sir. Any other questions? Okay. So, my dear friends, we'll be having our class every Sunday, 1 to 3. I will go back to the page and update a couple of things. So please occasionally check back and then see the updates. At the end of every week or every week's lecture, you will need to how do you call it? Go to the page and then do a small exercise. Okay, so there will be some exercises on the page at the end of every week's lecture, and then you will be asked, or you will need to go and then do some small exercise. Okay.
Okay, sir.
Okay. So I'll see you, God willing. The course rep has my contact information, so kindly reach out. I'll try and remember your contact information. So kindly reach out, and then if you have any questions. Okay. Thank you.
Thank you, sir.
Okay. Bye-bye.
Bye. Oye, oye, acá.